morning, good afternoon, and good evening, wherever you are. Thank you for joining. At CIQ, we're focused on powering the next generation of software infrastructure, leveraging the capabilities of cloud, hyperscale, and HPC. From research to the enterprise, our customers rely on us for the ultimate Rocky Linux, Werewolf, and Aptainer support escalation. We provide deep development capabilities and solutions, all delivered in the collaborative spirit of open source.
Yay! This is my favorite time of the year, of the month, is when we get together with the Research Computing Roundtable. I think it's been a little too long since I've seen you guys. So thank you so much. We're going to go around and do a little intros, and then we're going to dive in today's topics. And if you guys have any questions, just jot them in the comments. Even if you're watching later and you're not actually watching the live version, still jot down the comments. We make sure that we go back and answer everything that you have, or you can just go to CIQ and give us a direct message. We would love and appreciate a like and a subscribe, and even click that little bell that says notifications. So we like to come on here and give you guys lots of value of all the cool things that we are doing here. So without further ado, thank you everybody so much for being here for our Research Roundtable. My name is Rose Stein. I am your co-host here at CIQ. I've been working at CIQ it's been a couple of years now. I feel like coming up, right? A year and a half. Been working with some of the good folks at CIQ for several years at a couple different companies. And so it's really exciting to come together and talk about all the amazing things that are happening in the tech world. This is the coolest. I mean, Gary, can you even imagine yourself at 5 years old, imagining what the world is like right now?
Not at all.
So introduce yourself and tell us a little bit about what you work on.
Yeah, my name is Gary Jung. I'm the Science IT Department Head over at Berkeley Lab, where we manage the institutional high-performance computing and scientific computing. And I also have another role as the manager of the high-performance computing program for institutional computing down at UC Berkeley. So I've been doing this for 22 years.
It's really cool. I just have a question about your background. I imagine that's a picture. You're not actually sitting there, right?
Well, actually, that is a picture of our data center. And so that is not a random background. It's actually a picture of our data center downstairs.
Okay, so how loud is that data center? Like when you walk in, would I still be able to hear you as clearly as I can right now?
Yeah, it seems a lot louder than if you're there, but I actually brought in a decibel meter, and it actually didn't read that high, but it sounds loud when you're in there. You do have to kind of talk really loudly to be heard.
Forrest one time built us a little like online web office, and there was a secret room that looked just like your background, but he added in the sound like that, the hum of the computers working. Do you remember that, Forrest?
Yeah, I put like a link, like you can make the objects like link to videos, right? So I made the server racks link to a video of like just like a bunch of fans on YouTube. So if you wanted to, you could go in there, like turn the YouTube video on and get like the real experience of having to yell over some fans to talk to your colleagues if you really like needed that experience while working virtually.
There's also something about a hum in the background that actually helps me focus as well. So I would often go into that little room.
I'll just so people who are curious. So the blue lights are from the active rear cooling liquid cooled doors that take off the heat, and then everybody sees a little bright white light at the bottom of the racks, and that's the CDU or heat exchanger for the direct liquid cooling to the processors for the servers in the rack. So some people now know what they're seeing.
That's awesome. Thank you. All right, Mr. Alan Sills.
Hey there, just Sil. There's just one of me.
Oh, still. Thank you. Sorry for the extra S.
It's all the opera singer's fault. So I'm Alan Sill. I manage the High Performance Computing Center at Texas Tech University and System, and co-direct Industry University Cooperative Research Center in cloud and autonomic computing, spanning multiple universities for the National Science Foundation. And I'm excited to announce that as of the 25th of June, co-direct the NSF's new renewable energy powered cluster under the Advanced Computing Systems and Services program. A new 5-year project that we are getting started on. Solar and wind power, battery storage, working on ground source heat pumps.
Congratulations. That's big news. Thank you, Gary. Or sorry, Alan. Okay, Jonathan, you want to introduce yourself?
Yeah, thanks, Rose. So I'm Jonathan Anderson. I'm an HPC engineer at CIQ, and my background's in academic high-performance computing. I've done systems administration, systems engineering for like compute clusters, storage clusters, that kind of thing. Although at CIQ, thanks to Fuzzball, I've been falling deeper and deeper into a Kubernetes rabbit hole these days, working on provisioning stuff for on-prem Fuzzball.
Yes, and thank you for all of that work. Thank you, Jonathan. All right,
It's
Mr.
always
Forrest.
cool to learn new things.
But it's cool to learn new things. I think Dave too. Dave Godlove was telling me because I think he's doing some of the documentation for Fuzzball, and I was like, "Oh man, like that sounds awful, right?" To like to go from like putting things together and code and figure things out for people to like doing documentation like full time as your job. Like, I'm so sorry about that. And he said, actually, it's kind of cool because he's learning something completely new, and like nobody really knows the product more than the person who's doing the documentation, right?
Hopefully.
Oh, well, yeah. Fair point. No pressure, Dave. All right, Forrest. Hello.
Good morning, everyone. Great to be on the webinar again. My name is Forrest Burt. I'm a technical sales specialist here at CIQ. I worked for a long time in engineering, about 2.5 years at CIQ. I was solutions architecting and systems engineering and all types of stuff in the HPC sphere. For another 2.5 years before that, I was one of the sysadmins at Boise State University. So working out there on their HPC systems, along with like alongside Idaho Power and the Idaho National Lab and that type of thing. Yeah, I, like I said, do a lot with academic National Lab HPC stuff. And increasingly these days, I'm kind of specializing, much like how Jonathan says in Kubernetes, I'm kind of going down the AI rabbit hole. We'll see how that all turns out, but yeah, great to be on.
You know, I remember 6 years ago, people were telling me that Kubernetes is the next, you know, the next great thing, the next big thing. We want people that understand and know Kubernetes and everything. And then I didn't hear about it for a little while. And now all of a sudden it's back again. So thank you guys. That's good work you're doing there. All right, Alan, you want to start off here and just kind of tell us a little bit about what workflow portability and workflow definition languages are to you?
Oh, wow. Well, it can be highly discipline specific. And what constitutes a workflow is kind of an amorphous concept when working with researchers. Anything that can produce a, you know, hopefully organized path through a set of tasks might be considered a workflow. But there are formal workflow management tools, and again, they can be highly specific to the discipline, or they can be very general. Let's just pick an easy one. You might have a large number of identical tasks, and really there's just a little variation in the input parameters or maybe the call sequences to call each subtask. So a typical thing might be to use a scheduler, a batch scheduler with the ability to handle array jobs. Slurm has the concept of array jobs directly, and you can just say, you know, here's a set of things I want you to do them, you know, n at a time with the following algorithm for changing the inputs, and I want you to store the outputs with you know, file names that mean something in that array sequence. If any one fails, you can repeat it. So that's a typical thing that we'll do, and especially if you have tasks that don't take much time to increment through. So, you're doing some sequencing step or you're some image processing step, and each step takes a little time. So you don't want to burden the scheduler with submitting, 15,000 of them. You want to submit one array job that does 15,000 things for you. There are much more sophisticated workflow managers, even tools that are designed to handle tasks that, again, are discipline specific. So, SnakeMake and our parallel tools might be in that category. Let me throw it to Gary and see what I've left out. I'm sure it's a lot.
Gary, fill in the blanks.
Well, yeah, for me, workflow manager is almost like a scripting language to glue together a bunch of tasks that will, like, say, do movement of data, do processing of data, maybe even I've seen it like used in the cloud where people are gluing together workflows in the cloud where they're running. And the one I've seen was in like the one I can see that I've seen recently is like a genomics pipeline where they're going to be dispatching it to, whether it's going to be the on demand or it's going to be a spot instance, and you can kind of like write that into the script. So to me, a workflow language is like a scripting language, and so just to help glue together that pipeline for you so that it automates it.
And what about you, Forrest? When you think about workflow portability, what comes to your mind?
Ultimately, it's just that ability to take something that, say, a research group has built and deploy that out easily to everyone in it. Ultimately, the thing that I think of is, for example, time to results and time that it takes to get people up and running on things. I think workflow engines in any form are a useful way to chain together long sequences of tasks that ultimately are all part of one whole that should be run together. In general, for me, the biggest and most powerful thing about them is kind of looking at how a well put together set of workflows that are easily templatable from person to person in a group can bring a research group, like I said, online much faster just by being able to onboard people and stuff like that much better.
And Jonathan, is there anything that you want to add to that? And then specific more, can you explain what a workflow definition language is?
Sure. So, and Alan touched on this a little bit, maybe Gary as well, that, when you're in a specific research or scientific domain, or really any application domain, there's common tasks that you want to do in that domain. And a workflow definition language is often a domain-specific language that makes it easier to talk about the activities and the processes that are germane to that field in a more natural way. I don't have a lot personally of experience with that kind of domain specific workflow definition because I'm a sysadmin type person. I'm a systems person, not a domain scientist. The closest I get to is infrastructure automation, something like Terraform or Ansible. These are systems that allow you to say in kind of optimized ways how you want your infrastructure to behave, and I would compare that to how you want your scientific application to be run on a compute resource. To me, one of the best hallmarks of that, the best way for it to be, and Gary was talking about these being scripting languages, and often that's true. As a systems person, I mostly interacted with that as people writing bash scripts that ran persistently on a login node to watch a queue policy and try and feed it jobs to work around queue policy whenever possible. But to me, what I look for in this kind of language when it is apropos to what I'm doing is declarative languages rather than imperative or scripting languages. So instead of saying do this, then do this, then do this, I want to say this is the work that needs to be done, and these are the dependencies between that. We see a little bit of that in the way Fuzzball does its workflow definitions, people on the infrastructure side may be familiar with tools like Puppet or Salt. These are very declarative in the way they work. There's no defined order in I put the tasks to be done in this file. The order that they're in there isn't necessarily how they should be done, but you can say these have to be done before these, and the dependencies are specified as a part of the data. And I think that kind of declarative definition of your workflow, or really in many environments, aids that portability that we're after, that kind of write once and run anywhere, because where you get into the weeds of making something not as portable is when you're caring about how it gets done, or in what order and which parts of a system should be used to accomplish what you really want, which is please use this application to generate some result from some input. The user shouldn't have to care like how a given environment or a given system is going to accomplish that. And there's always leaky abstraction. No language is perfect, but to me, that's the goal for this kind of a specialized language, is making it more declarative rather than imperative, so that you can then write an execution engine for that language to run wherever you want your workflow to run.
And how has... Oh yeah, go ahead.
No, I want to pick up on that. I think I put in our private chat here. It didn't return. The grid essentially was so the grid, the early coordinated scientific computing across multiple resources, was essentially not a workflow management piece of software itself, but it was a container for such things. Lots of we called them virtual organizations. Astronomy, particle physics, biology would set up their own organization-based tools. And the idea of the grid was access to clusters all over the world in a shared way, so that you could direct workload to, maybe you'd send the code to where the data was available, maybe you'd send the data to where compute was available. And so the compute grid was sort of what preceded the cloud in terms of organized workflow. So, I think the question, as I think about it, really had to do more with the formal definition of workflow portability, which would have been focused on the standards that were developed. I think there was something called open workflow language that a lot of people tried to push onto the grid, but most of the time individual organizations would come up with their own. I think a related concept is data portability, and probably workflow portability is the combination of data portability and code orchestration. I would guess that would be a good way to phrase it. Orchestration being, how do you, what's the recipe by which you deploy things in which order to get a set of tasks done. And you couple that with data portability, you probably have workflow portability.
So it's a good segue into kind of talking about containerization. I'm wondering, Alan, at Texas Tech, how prevalent is container usage? Is it mandatory? Is it everywhere? Is it like 50%?
Well, that's interesting. That's a very good question, actually, because like most academic outfits, we're driven by the "is it on fire" definition of whether to work on something or not. And the second question being, no, is it really on fire? Then you work on that. Often we would throw containers at messy sets of code that were difficult to get to integrate to the rest of the cluster. And of course, that's not really, a purist approach to it, right? It's not at all systematic. And you contrast that with a lot of cloud workflows that essentially start from containers. It's a big difference, probably the biggest difference you're running into when you look at Fuzzball and Kubernetes. So we often will actually uncontainerize something once we understand it, just in the interest of having it mesh with the rest of our software installation practices. You know, when you containerize something, you put it in a box, and you probably never want to open that box again. And again, not what the purists approach would be to the containers. And no, you shouldn't have static containers. You should have recipes for building containers dynamically, so they're always. Oh yeah. Thanks for the theory. I have. Is it on fire?
That's why you
Oh,
should
the
just be
best.
constantly burning your containers to the ground, so you have to rebuild them all the
Exactly.
time.
That's correct, but not what we typically do.
I like your style, Alan. Oh, there's a best practice? Yeah.
My script just wipes CM shared containers every morning.
Yeah. We have a special meeting for those folks every morning that I somehow never make it.
Oh, that's awesome. So kind of the same question for you, Gary. What is the adoption of containers around the lab and at UC Berkeley?
You know, we're pushing towards it, and it's usually by domain where it gets the push. So, for example, recently the Joint Genome Institute, which is a user facility at Berkeley Lab, used to do most of their computing at NERSC, which is a national supercomputing facility, and instead they needed their own system in addition to NERSC. So we built them a fairly large local system for their work. But one of the things that we did is in transitioning the users over is that they had come up with this thing to run everything on containers in order to simplify the management of the system. And so for people to be able to use it, in order for people to get onto the system, they had to convert their code to containers. And so this is for a couple of reasons. One, that it makes it easier to manage a newer system. We don't have to build in a lot of these older dependencies. And then the other thing is that because they need so much computing, as a lot of research projects, is that they actually have a portfolio of computing resources outside of Berkeley Laboratory. So they use, for example, PNNL, they use the cloud. So having it in container makes it easier for people to move and run their jobs across this portfolio of resources. So that was one of the big reasons for doing it.
That's awesome. I think we got a question. Richard Adams, thanks for being with us here today. And he says, what are the major things that differentiate HPC schedulers from other common workload schedulers such as Kubernetes or Airflow? Not everybody at once. I'm going to pick on somebody. Jonathan.
Great. So I don't know Airflow, but assuming for just a moment that it's at least somewhat similar to Kubernetes. So at least in that binary, HPC, was it schedulers? Yeah, that's was the word we're using. HPC schedulers prioritize very different things from a Kubernetes or cloud native scheduler or workload manager cluster scheduler thing. So in general, an HPC scheduler resource manager is going to prioritize bare metal performance and batch compute. So anything that gets in the way of the fastest that your hardware can run is something you at least want to be able to turn off, probably have off by default. And then the goal tends to be to take an application with some input, run it to completion, and then deliver the output. By contrast, Kubernetes is more about resiliency and scalability and isolation over performance. So, and then it's services rather than batch compute. So a process running in a Kubernetes cluster tends to start and then have no expected end date. It just runs forever. It's a web server or some kind of thing that's expecting requests and responds to those requests, or a database server, that kind of thing. But then that you could get away with. You can run batch in Kubernetes. You can do it. But it's expecting those services to be things where if something goes wrong, it wants to be able to start it up again really quickly. Or if you have two things that are running in the cluster, it wants to have full control over those two applications being able to talk to each other. So there's a whole network indirection layer between them. And all of those services, all of those capabilities that add up to resiliency, scalability, get in the way of that bare metal performance. And you can turn things like that off and get closer and closer to what performance you would want out of an HPC environment in a Kubernetes environment. But the more you do that, the less it looks like Kubernetes. And so much like the domain-specific language conversation we were having earlier, where sometimes it's good to have a language specifically for dealing with a given scientific domain, the same is true here. Kubernetes is built for a given purpose, and it's really well tuned for that purpose. And there are other schedulers that are built and tuned for the purpose of running on the most expensive computers that you can, because if you lose 1% of that performance, it's untold amount of money that you're leaving on the table that you spent on all of that expensive hardware, where resiliency wasn't really the value proposition. So that doesn't mean there aren't things that the two can't learn from each other. And that's a big part of the Fuzzball story, is trying to, from an HPC perspective, look across the fence at the Kubernetes and cloud native world and see what we can learn from that experience and that practice, and then hopefully bring some of that HPC expertise that's baked into Fuzzball that might be applicable in an enterprise or cloud native environment.
Yeah. Did you want to add to that, Alan?
All right. So one has to understand that there are schedulers at every level, right? The kernel has a scheduler. There, so there's the specific question is asking us to compare, as Jonathan said, Kubernetes. I'll talk about Airflow in a minute. That was aimed at microservice ideas and scaling those microservices to HPC, which is basically trying to keep a set of resources fully occupied for the maximum productivity, and to schedule such activity according to various criteria. You can set priorities among different types of workloads. You can look at how long each task will take, but a more predictive approach to it. Whereas in Kubernetes and many cloud-oriented workflows, you're often responding to dynamic conditions. It's pretty rare these days that people run HPC clusters in a way where you interrupt workloads to get other workloads done. You try to avoid that just for continuity of service and productivity. Whereas in cloud settings, it's essentially the rule, right? You basically say, I have to respond to this dynamic situation. I need to scale a whole bunch more of these microservices, or I need to, migrate some of the workload to another cluster or to another environment. Now, Airflow comes from a series of several related Apache projects. It's really aimed at data pipelines. So here, the predictivity, is that a word, comes from having a set of organized data processing steps and wanting to just create a pipeline in a relatively, low-code way to process that pipeline. So it's really kind of a different beast entirely.
Yeah, it was a really great question, though. I mean, I think that's, Jonathan, you mentioned it briefly about Fuzzball, and that's kind of the idea, is to bring the benefits of both different types of scheduling and computing kind of together in one. So that's, it's a great question. Is there any more about that you guys want to touch on before we move on? Sounds good. Okay, so what about ARM computing? Tell me, pros and cons. Who's got some experience with that? Forrest, are you in the know with the ARM computing?
ARM is fun.
All right, that's our one soundbite, right? That's like our ARM is fun.
There's your YouTube short there,
There you go, exactly.
The thing, so ARM has been the thing powering everyone's phones and little, micro devices for a long time at this point. So ARM is a lot closer to everyone than most people realize. It's just been here in recent years that with some of the extensions that they've made to some of their instruction sets, with like ARM v8, I think ARM v9, I think is out now. I don't quite remember. I know ARM v8 is at least out there. But with some of the, I think of like the Neon SIMD instructions and stuff like that they've built into it. With things like that, and just in general, the power cost of those GPUs, or not GPUs, CPUs being so much different than our standard, x86 64, it's like I said, it's an architecture that's been widely accepted for a certain type of computing for years, and that's mobile computing. I mean, it's ubiquitous. Nobody puts the same type of CPUs that we have in our servers into phones for the most part. It's just the last couple of years, advancements have kind of allowed it to become more of a server architecture. And so now we see a lot of places like NVIDIA even building these really high core count chips that are all based on ARM. I think ARM is really, really cool. I think it'll have a few years kind of in the light where everyone, it's kind of popular on servers. Things tend to move glacially slow with the acceptance of new architectures just because it's such a huge thing to take the ARM standard and build chips for it. That's a huge investment in time, money, engineering, etc. So it really takes a long time for an architecture to become proven, especially for building them to servers and stuff like that. So I think ARM will probably have a couple of years here where it's very, very popular, but there are things like RISC-V that are coming out that are kind of increasingly starting to eat its lunch. And I think that, just kind of in general, much like how with kind of GPUs right now, where, hold on, maybe we don't just all have to use the NVIDIA GPU. Maybe we can build something better than this. We're kind of seeing the same thing with CPU architectures where it's like, well, maybe we don't all have to use x86 64 forever. Let's, take a look at what else is out there. And so we see ARM kind of becoming popular. We see RISC-V becoming popular. I think we'll see RISC-V is a good contender, but we might even see something else that kind of comes out here in the next few years. I think it's a great architecture. It'll have a few years that it'll be really, really popular. But if just with kind of how we're taking a step back and more broadly looking at computing and how we're building things at the moment, it's possible something else like RISC-V will come up that will eventually supplant basically everything.
Go ahead, Alan.
So I put a couple of things down that we're building just to train my students. I've started, as you maybe heard in previous calls, building these little mini clusters. I now just think, whenever I hire a new person, I'm just going to hand them one. Little $600 is typically what we're spending on these 4-node fully decked out cluster that runs the same as our, a few $1 million worth of hardware in the machine room. I'd rather they mess up on that than on the main cluster, right? So we built Raspberry Pi ones first, and then we went on to other types. Our favorite one right now is an x86 board called Bradska RDXA, and then we can build, $70 or $80 a board, and so you can just build a nice little cluster. But we have built RISC-V and RK3588 ones. Of course, Raspberry Pis and RK3588, it's our ARM processors. And one of our master's students will be, within the next few months, I hope, getting good progress on his master's thesis to compare the performance of these things. On the higher end, ARM is the basis of a lot of the fastest stuff out there, including NVIDIA GPUs, right? So, and a lot of high-speed chips. The Graviton 4 was announced not long ago by AWS, and Phoronix just published a comparison of the performance of the Graviton 4 with other high core count processors, where it beat some in some measures, and was behind in others. It was sort of mid-pack, below the fastest AMD chips, but above Intel. Intel coming in third a lot lately.
All right, so I think we have a special treat here. Ha ha!
Oh yeah, our little cluster. Yeah, you're just building lots of these now, and so this one's happens to be power over Ethernet powered with a little PoE switch in the bottom, 4 worker nodes, and then the connectivity to the external network and keyboard and mouse. These are fun, and it runs Rocky 9, Werewolf, Aptainer. We're installing stuff with SPAC. It actually is running the exact same software as our main cluster, except it's a little ahead in versions. So it's actually this specific one was where we fixed the DNS mask setup problem, Jonathan. So
Nice.
we'll get that into the documentation pretty soon.
I either didn't know or had forgotten that you were doing PoE with that. That's really, really cool.
Yeah, it's a little bit tricky, but I think the future is that we will see lots of these things, and they'll be increasingly commodity items. As a training tool, they're just fantastic. But that's a little bit different from the original question about ARM processors. But we're seeing them on the low end and the high end. Let's just say that.
I want to jump on that specifically because that to me is what makes ARM so cool. Like we've had multi-arch. Let's just talk about Linux for a minute. We've had multi-arch for a while, and in my experience, in my professional experience anyway, that's mostly been about x86 and PowerPC, like historically. And there were, if you were running on some IBM Power stuff, then you needed a PowerPC version of your Linux distro, and otherwise it was an x86 build. But that made the multi-arch nature and kind of that portability aspect of Linux as an operating system and all of this software as an ecosystem very kind of cordoned off to that professional realm. People don't have IBM Power systems lying around. The really cool thing to me about ARM is that it is interesting as a kind of a production, is increasingly so interesting as a production high performance computing architecture or server architecture. All of these things, there's a lot of cool stuff about it, but because it's come up as the processor in your cell phone, like Forrest was saying, or the popularity of the single board computers with the Raspberry Pi and its clones, it means that this experience of having to run computing across multiple architectures is accessible to people in a training environment with a training cluster like what Alan is building, or people may have had their first computing experience be a little Raspberry Pi board rather than an x86 PC that they built because maybe they just have a MacBook and they want to build something to tinker with, and it's a Raspberry Pi. And like the in my mind, the secret to portability is necessity. And if everything you run is an x86 computer, then you're not really portable. It feels like you are because everything you have runs everywhere. But the minute you get outside of that ecosystem, maybe things will fall apart. It's never been tested. And because people interact with both x86 and ARM, and hopefully in the not too distant future, RISC-V, and there are training and development boards available for that as well, I really am excited about getting away from this one architecture for everything state that we're in to test the portability of our systems, test the portability of our applications and our code, because that's the only way it really will be portable and work once a given architecture goes away, is to have already demonstrated that you can run those things in multiple environments.
So a question for all of you then. As we've seen, the top-end exascale systems all are integrated CPU, GPU systems. And those take a long time to port code to, as opposed to just a different architecture of CPU. That's, a nuisance for a while, but then the compilers get working and off you go. But it's a lot more work. So by the way, one of the other awards in this same Advanced Computing Systems and Services that we got our renewable energy powered cluster funded by, one of the other awards went to San Diego Supercomputing Center, and they've announced that they're using an HPE liquid cooled system, and they didn't say what it is. But if you look at the recently deployed, and they said they'll be using MI300As. So if you look at recently deployed liquid cooled MI300As, it's El Capitan, and just the test systems, just the single racks test systems for El Capitan. There are 3 of them in the June 500 top 500 list, the June 2024 top 500 list, and all 3 of them benchmark at 19.4 petaflops in a rack. So you can get tremendous productivity in terms of CPU power. But what's the catch? Well, it took the whole exascale compute project, a multi-year project, to port a few dozen high-end applications to run on these things. And so our friends, my hat is off to them. I admire it. I applaud it. This is a fantastic project. I'm just glad they didn't beat us out of funding, and they also got theirs funded. But if you look at their project plan, it's 3 years of development and 2 years of user services. This tells me that they're going to take it. I'm just interpolating here, so apologize to my SDSC friends if I'm getting it wrong. But I think they're going to tackle porting the rest of the applications to this platform, this CPU GPU platform. And that shows you how much work it is. So if you really want to go for the top performance, it's a lot more work than just changing CPU architectures. So how are you seeing this play out in your requests? I mean, at CIQ, are you getting requests to support such architectures? Gary, do you see this impacting your HPC?
No, in fact, I was going to stay quiet during this section of the talk because we haven't really looked at ARM at all. I agree, just the amount of work it would take. I mean, we have so many other things that we have to do that to take staff time and put it in that as opposed to other things that could be advancing science. Can't do it.
Jonathan, Forrest, did you guys want to speak to your experience?
I don't have direct experience with porting GPU applications. I may have done a Hello World GPU application at some point, but I don't know. I still feel unsettled about the state of GPU code portability, and I think that that's a big part of the issue. And I don't know how we get where we want to be, where, right now you can write a C application and with pretty good success compile it for ARM or x86 or RISC-V or whatever, and it's fine. I don't know how we get to that with GPUs, and it may just be that the current state of the industry there is just in such flux that we're just in the hard moment, and it's not going to be like that for a little while. But I don't know. I don't have any real experience with it.
I agree. I think like 98% of all data center GPU sales were NVIDIA in 2023. So the fact of the matter when it comes to like the basics of GPU code is that if we're porting GPU code, we're probably porting it to CUDA at this point because that's what just everyone is using. It's a no-brainer if you're building a new data center to go with NVIDIA right now, because if you put a bunch of like AMD in there, you're going to have a bunch of angry researchers that are like, well, why does my code not immediately work? Why are these not NVIDIA GPUs? In general, on a higher level, my question would be is how portable are all workloads to GPUs in general? The biggest difference, the thing that differentiates them is, with the CPU, we might have, under 100 cores, but those cores are all incredibly sophisticated with pipelining, multi-threading, all that type of thing. They're incredibly sophisticated. There's a lot that they can do. With a GPU, we might have a few thousand little tiny cores, but they're not nearly as sophisticated as a CPU's cores. They're just little tiny, basically just like multiplied processing units to do just basic arithmetic, that type of thing. So ultimately, and when you look at, for example, how long, the problem of like how fast can you actually get data to the GPU? Is it actually, a fast enough network path between there that offloading computing to the GPU is actually worthwhile in the end versus the time you're going to take to even get data there. So it comes down, like I said, for me, it comes down to kind of the practical considerations of what workflows can actually be ported to GPUs. Because like the classic example, the thing people always ask me when they, we're all chilling out or whatever, is, well, why do we actually, I've been asked a couple times, well, why do we use like GPUs for AI training instead of CPUs? It's because of that right there. When we train, the neurons in an AI, the very high level, when we train the neurons in an AI model, most of those little calculations are just really, really basic, tiny, long sequences of additions and multiplications. It's really easy to map that to the thousands of cores on a GPU and have it be much more efficient than it is to essentially waste all the sophistication of a CPU with pipelining and multi-threading and all that type of thing. And so that's why, for certain workloads like AI, where we're basically doing a whole bunch of really small, simple mathematical operations, we don't need, for some things, sorry, I'm rambling, but for some things, we actually do need double precision floating point numbers, like what we test clusters on when we do HPL. But they increasingly find with, like GPUs, you only need, 8 or 16-bit, numbers, because it's just not, the precision is just not necessary down to a certain point. So it's really, two entirely different flavors of computing. It'll be interesting to see who ends up winning the GPU thing. Like I said, with CPUs right now, we're kind of looking at different architectures. The same thing is going on with GPUs, where we have Intel, AMD, these other places tossing their hat in the ring, but also Cerebras and all these other places. They're trying to build something better than the GPU specifically for AI training. Like the Cerebras chip, all it does, it is meant to be like a grid engine of like millions of little processors that all just do those little tiny mathematical operations. So then it'll be interesting to see what goes on. This is kind of one of those topics that can get me a little bit fired up. I'm very interested in kind of how workflows and workloads actually map to the underlying hardware devices. And so yeah, ultimately for me, it comes down to what workflows can we actually port to GPUs and still have it be, with data transfer times and stuff like that, be efficient and worthwhile to spend, because it takes a lot of time to do that. So.
Okay, I have kind of like a side question, you guys. If you had to guess, how many clusters do you think get built, like in a year? New clusters.
So I've been here on the side trying to estimate the current power costs from all the NVIDIA GPUs in the US. New clusters in a year?
Yeah.
New named clusters of a significant size in the United States, I would say it's probably less than, I don't know, guys. Everyone might immediately disagree, but I would estimate it's like 50 to 100 new significant deployments per year throughout the US of actually like named clusters that aren't just like, a closet cluster in the engineering department's back office, but are actually like planned, named, large deployments. I don't know, I'd say it's got to be at least 50 to 100.
Oh, what are you saying? Alan's little mini cluster doesn't count?
Well, I'm saying there are a lot of small things like that, I'm saying, that are like, mini,
Yeah.
Like I said, Boise State, every once in a while we would discover, small clusters people had built. But I'm saying just like when it comes down to things that, a huge institutional planning board is going to sit down and budget out, and, we're going to go talk to Dell and do things like that. They're most definitely clusters. I've always defined HPC as basically doing anything beyond your standard computing resources. Like if you are looking for more computing power specifically, you're doing HPC. So it definitely counts. But I would say large scale deployments, like I said, of like named clusters. I'm thinking about at universities, at different places like that, because everyone's usually on like a 2 to 3 year cycle on new clusters. So I would say it's probably 50 to 100.
So, I mean, somewhere listening to this podcast perhaps is industry consultant with his head in his hands thinking, this is my entire, have you not looked at any of my output? I'm thinking of Intersect 360 or any of the HPC market analysts that make that their business to understand this thing. So yeah, there are summaries that are put out periodically. I was just looking for the one from Addison Snell, who is someone I think really has a pretty good grasp of market. There are some that I disagree with. So I guess I want to ask a meta question, which is, is AI a bubble? Is our GPUs a bubble? Will it all get submarined by quantum computing at some level? I don't know. But what's a cluster would be my answer to your question, Rose.
Okay.
Let's understand that all of the HPC market in academia put together is, 1% or less of the amount of computing deployed by industry. And data centers are typically built and measured in acres these days, and powered in numbers that are order of 100 megawatts each. So scientific computing, shares a lot with these things. And actually, if you'll forgive me a little ad, that's one of the things that our little renewable energy powered cluster is going to study. It's not new to power clusters or industry computers with renewable energy. They do it whenever they can, just for cost reasons, but and also for marketing and advertising reasons. But it still leaves problems. A lot of our clusters need a lot of care and feeding, and running those remotely so that you can put them out at wind farms and solar arrays. That's one of the things we'll be studying. So we share a lot of technology and interests with industry, but I'm actually disappointed. People often come at the HPC versus cloud thing from that point of view, is, let's just all do it in the cloud, and they get their bill and they say, that's nuts. What are the other ideas? So we ought to share a lot of technology, and we ought to share a lot of cost savings, but finding those overlaps is remarkably difficult.
My understanding is that the industry use of AI type hardware, which is very much like the HPC hardware, will dwarf the current HPC market. And so I remember hearing somewhere that it was over 30 times as large as the HPC market.
That's not surprising. And that's, when it comes down to, is AI a bubble? I think certain use cases of it are a bubble. I think it's, I see a lot these days where people kind of generalize the AI to, crappy AI art and chatbots and stuff. But the fact of the matter is, it's so generally applicable to most things. The most use cases in AI are probably things you never see. It's, Samsung's chip design AI that they've spent extensive time training on all of their best designs to assist their engineers. Span that ad infinitum across basically any industrial company, from computer companies to chemical companies to whatever. I'm sure all these places right now, like I said, it's fun that we have these stupid chatbots and these crappy AI art taking over everything. But the fact of the matter with AI is that the real use cases are things most people never see. It's industrial use cases, it's private businesses that are utilizing this as a part of their daily design processes. And that's what's going to end up pushing it, is because, it's fun that we can have, as Alan calls them, these little plagiarism engines that can endlessly, rechurn the information that they know in any way, shape, or form, in any, funny little accent or whatever that you want to put on it. But ultimately, the most hard-hitting use cases in AI are the fact that it's so generally applicable to essentially every industrial process. And everyone right now is trying to get in on that to some extent, trying to figure out if they can actually integrate that into their processes. We'll see how that sticks for people, but so far it just turns out it's so generally applicable that we are either in a bubble or we are in like a new era of research and development and engineering. We'll see how it turns out for us.
Yeah, fair. I mean, my family owns a restaurant, and for years now, we've been using AI technology to kind of map input and output of actual food, right? So there's like, they weigh everything that comes in and everything that goes out. And then that feeds into some system that they do. I'm not really sure exactly. I guess I should ask more questions to reduce waste, right? Like one of the largest wastes, at least in the United States, is food. I mean, it's incredible how much food we throw away. So to reduce waste, which also reduce costs, which increases profit, there's always reasons and motivations behind things. But you're right. There's a lot of AI kind of technology behind the scenes in everywhere. So thanks for bringing that up.
And ads. One final thing, ads. You would
Advertising, like marketing.
Yeah, you would not believe the amount of power in watts, cost in hours, and time that is spent entirely on just finding new and inventive ways to serve ads to people. And you go scroll through your Instagram, and the algorithm shows you a bunch of stuff that is almost what you've been thinking, a few minutes prior. That is all GPUs. That is all AI. And it's like that's been for years one of the biggest hidden AI use cases is you would not believe how much time goes into improving the experience of online advertising just so that I can install uBlock Origin and render all of those efforts null and void.
I know. I really like targeted marketing, actually, because I'm like, I was just thinking about that. Yes, that's exactly what I want. So we are kind of up on time here, guys. We could probably talk forever and ever. But Gary, do you want to kind of like wrap up with some final thoughts here?
No, I was looking forward to maybe talking about the power and cooling for AI. And
I know. Do it real quick. You got it.
Yeah, so if I was just going to sum it up, I would say that everybody's designing for about 120 to 140 kilowatts per rack right now for the new AI machines. And for people that are thinking about data center stuff, you could do about 35 kilowatts per rack with air cooled, up to 80 with a rear door cooling. And in order to get those other numbers, you're going to have to go with direct liquid cooled. So people should be looking really high density racks, 415 volts, direct liquid cooling, and rear doors would be a good solution, conventional solution for getting there.
So is that liquid cooling where it kind of goes around, or is it the liquid cooling where you actually submerge it?
It is the liquid cooling where they replace the heat sink on the processor, very much like gamers have been doing on their PCs for years. It's just more of an industrial version of that set up in a rack.
Both types exist, both immersion cooling and, but I like Gary use. I hate rear door heat exchangers. They're just air conditioners you hang on the back of your racks. You only do it for space reasons, but yes, direct liquid cooling to the chips is necessary. The interesting stuff lately is single phase versus two phase direct liquid cooling.
So yeah, we use both.
Solution.
Yeah. I think the thing with the two phase is that at least the one we're using uses a PFAS, which is one of those forever chemicals.
Yep.
So that could be an issue down the road.
That is, there are some companies specifically targeting getting rid of the PFAS, polyfluorinated something or other. That's bad for you.
This is new to me. Is the two phase where you just have a transition between liquid and gas at some point in your cooling?
Yeah, it's all subatmospheric, but the liquid actually boils in the cold plate.
Right.
And it's taken off as vapor and then recondensed elsewhere. It turns out to be remarkably touchy about the temperature that it recondenses. So at first I thought, oh, great, mini splits for my data center. I'll just run the heat pipes outside. But no, they like depositing their heat into well-controlled conditions, water or air. But the interesting thing is you can get up to 1,200, 1,500 watts per socket, which imagine if that were a light bulb. So, that's a lot of power.
Is it all still mostly warm, or is it chilled at all? Like, do you have any concerns with condensation or anything like that in the environments that you're running in?
So we don't see any condensation, though, because our building only supplies chilled water. We had to put the coolant distribution unit, we had to insulate it to keep it from condensing. It's normally designed to deposit its heat into room temperature water. So we haven't had any condensation issues within the nodes. I think one of the I'm trying to remember the company. I think it was Isotope, ICETOPE in the UK that was specifically advertising that it doesn't use PFAS and it's two-phase coolant.
Yeah, we use warm water with ours, and then what we do is it comes out of the rear door heat exchanger, and then it goes into the heat exchanger for the direct water cooling. So we're able to increase the delta T on the water loop and make it much more efficient.
So you have rear doors and direct to chip?
Yeah.
In the same rack, or it just in different environments?
Same rack, because
Wow.
then we can put more heat into the same water, and makes it much more efficient.
Cool.
Yeah, so let's be clear. The purpose of the rear door heat exchangers, partly for convenience to make the cooling near where the heat's coming from, but just to keep the ambient air in the hot aisle to a reasonable temperature. So we don't have rear door heat exchangers on our liquid cooled system because we have adequate airflow and the ambient temperatures are fine.
All right, guys, I think we might need to have a whole, webinar on just this one topic. So less topics next time so we can kind of dive in a little bit deeper. But I so much appreciate you guys' time. It is always such a pleasure to see you, Gary and Alan. Thank you so much. Jonathan and Forrest, always a pleasure. I hope you guys have a wonderful day. Thanks for being here. Remember to like and subscribe. And if you guys want to know more, talk to us a little bit about what we're doing here at CIQ and all the cool stuff, including Fuzzball, reach out to CIQ.com. All right. Have a great day, guys. See you later.
Thanks.